Okay, let's do an example using all three charts that we learned about. The relative roughness, the Moody chart, and the minor loss coefficient chart. Here we have two reservoirs, and their levels are 60 feet apart. And here at the first reservoir, the water, actually I believe the pump extracts water from the bottom reservoir up towards the top. So we can call this reservoir 1, and the water goes this way, comes up the pipe, and comes into reservoir 2. Okay? And here at the entrance we have just a regular squared entrance. We have pipe, and then we come to a, I believe, a fully open check valve. And then we go here, pipe, and then a pump. Pumps the water up. There's an elbow here. More pipe. It goes to another valve. And then here we just have a squared exit. Okay? And the question is asking, determine the shaft power needed to drive a 65% efficient pump to maintain a flow rate of 60 gallons per minute from the lower reservoir to the upper reservoir. Okay? And some of the givens. Let's write down the givens. These are givens in the problem. Okay? They're on my paper. The problem says that this pipe is a 1-inch diameter wrought iron pipe. Wrought iron pipe, okay? And so they give you the material of this pipe, so immediately you should think that we should go to the relative roughness chart, and we will in a second. So that's the first given. The second given is that the liquid that's traveling, it has a specific weight of 62.4 pounds per foot cubed, and it also has a kinematic viscosity of 1.21 times 10 to the negative 5th feet squared per second. There's two fully open swing check valves. I'll just call it valves. Swing check valve, so it's this valve right here and this valve up here. And then there's one standard threaded elbow, which is this elbow right here. It's standard threaded elbow. And there's one squared, I won't write that, but there's one squared entrance and one squared exit. So the water is actually going this way, okay? And the very first thing it said was that this pump needs to maintain a flow rate of Q is equal to 60 gallons per minute. And these units aren't something we like working with, so I'll change that to feet cubed per second, just to stay consistent, okay? So that's 0.134 feet cubed per second. And remember, if Q was equal to VA, the velocity times the area, then the velocity is going to be equal to Q divided by A. And the Q we found to be 0.134 divided by the area of the pipe. It's a tube, circular tube pipe, and the area is pi over 4. And remember, the pipe diameter was 1 inch, so it's going to be 1/12 of a foot squared, right? And if we solve the velocity is going to be 24.5 feet per second. Okay? Now, we have our Q, we have our V, we have kinematic viscosity. We can check to see if the water going through this system is going to be turbulent or not. And the easiest way to check that is to see if the Reynolds number is going to be greater than 2000. And remember, our Reynolds formula is going to be V times D over kinematic viscosity. And the V is average velocity, D is diameter, and nu is pneumatic viscosity. And the velocity we found to be 24.5. Diameter is 1 inch, or 1/12 of a foot, divided by 1.21 times 10 to the -5th. And if we solve the Reynolds number, we get, I'm going to write this down here, we get 1.69 times 10 to the 5th, which obviously is much greater than 2,000. Okay? And so if it's that much greater than 2,000, we know that if a Reynolds number for a fluid is greater than 2,000, it's turbulent. So this flow, turbulent. It's turbulent. We can use the Moody chart and the minor loss coefficient chart. Now, one more thing they gave us was the material. And it's a 1-inch diameter wrought iron pipe. And a wrought iron pipe is just another way of saying commercial steel. Okay? So for wrought iron pipe, since we're in US customary units, our epsilon is going to be 0.00015. Okay? So our relative roughness, or epsilon over diameter, is going to be 0.00015 over the diameter of the pipe. Now the diameter of the pipe is 1/12, or 1 inch, right? Because 1 inch divided by 12 is that the equivalent in feet. So the relative roughness is about 0.0018. Our Reynolds number is 1.69 times 10 to the 5th. And using these two values, we can use the Moody chart to find what our frictional factor is. And we'll do that in the next video.